Okay, this is section 2.5. We're going to go through the last three examples, 4, 5, and 6, of using the rational root theorem to find complex zeros and linear factors. So our first example is example 4, and this is my polynomial. X to the fifth minus 3x to the fourth minus 5x cubed plus 5x squared minus 6x plus 8. So I'm going to make my list of possibilities. Factors of 8 divided by factors of 1. Factors of 1 is nice and easy. Plus or minus 1, plus or minus 2, plus or minus 4, plus or minus 8. Okay? So I'll start with 1. It's the easiest one. It's going to be very important that we break this down. We keep using our result when we find one, because this one's going to end with some complex zeros, and you will not find them if you don't break them down. 1 times 1 is 1. Negative 3 plus 1 is negative 2. 1 times negative 2 is negative 2. Negative 7. Negative 7. Negative 2. Negative 2. Negative 8. Negative 8. 0. We found one that works. So I know 1 works. I should try 1 again on my result, because it might work a second time. Again, if I miss one here, this one I know has complex roots because I've seen the answer. But anytime it has some complex roots or irrational roots, if I miss one, I'm not getting the answer. So I need to check 1 a second time. 1, 1, negative 1, negative 1, negative 8, negative 8, negative 10. No, that's not going to be negative 8 or positive 8. So I'm going to try that same one again. This is the polynomial I'm now working off of. One, negative 3. That's a crazy looking 3. Positive 3, negative 4, 4, 2. That's not going to work either. I'll try 2. Oops, I missed my negative 2. One, 2, 0, 0, negative 7, negative 14, negative 16. No, that's not going to work. Let's try negative 2. 1, negative 2, negative 4, positive 8. That's 1. Negative 2, negative 4, positive 8. That works. I need to try negative 2 again. Here's my new one that I'm using. I guess it's down here. 1, negative 4. Again, I use the result. I check the same one that just worked. I don't need to check anything that didn't work. Since 1 didn't work twice, I don't need to check. I don't need to check it again. 1, negative 2 times 1 is negative 2, negative 6, 12, 13. No, not going to work. It's not a 0. I don't know why I wrote a 0 in there. Guess that was just helpful. So now I'm going to try the next one, 4. And here, I bring down my 1, 4, 0, 0, 1, 4. I've broken it down to a quadratic. That's x squared plus 1. So I'll put my list up here. Oh, not plus 10. Oh, it's plus 1, and that's going to equal 0. My list so far is 1, -2, 4. If I want to break this down, you can use the quadratic formula with b equals 0. Or it's pretty easy to solve this one with taking a square root. I'm going to square root both sides of this one. And when I square root, I must insert plus or minus. And the square root of -1 is I. So when I write this as linear factors, so here I've got my list, plus I, minus I. It's a fifth degree, there should be 5 factors. The solution that gives me 1 is x minus 1. Solution that gives me -2 is x plus 2. X minus 4 for the 4. X minus I gives me positive I. X plus I. Now, something that's really important. Complex conjugates. If you have complex numbers, or actually even irrational numbers, they must be the same thing, but the sign switched, because that's how we get, when we multiply complex conjugates, we get a real number. If you have non-complex conjugates, you get a complex number, and since you had no coefficients on the original, that were complex numbers, you better not have any coefficients with complex numbers in your result. Okay, we're going to move to example 5. Here I've got this polynomial. And I am told it has a root at 1 minus 2i. Okay. If I know it has a root at 1 minus 2i, guess what? I also know it has a root at 1 plus 2i. I could go guessing looking for real roots as factors of 65 over factors of 4. Kind of don't think it has it. I think they're all complex. And I can do this because I know this. I now know 2 roots, and I'll do synthetic division with a complex number. Yes, that can be done. And those 2 roots are going to allow me to break it down to a quadratic so I can find whatever else it has. So I'm writing this out. I have 4. I have 0 because I don't have an x cubed term. I'm purposely leaving a lot of space on this one. Bring down my 4. Now I'm multiplying 4 times 1 minus 2i. That's 4 minus 8i. This is a complex number here. Okay. Now's where I've got to do a little bit of side multiplication. 1 minus 2i times 4 minus 8i is what I need to do. I'm going to write it out off to the side. I'm going to FOIL, and then I'm going to simplify. So 1 times 4 is 4. 1 times -8 is -8i. -2i times 4 is -8i. -2i times 8i is 16i squared, which becomes a -16. -16 and 4 is -12 minus 16i. That's what goes here under the 17. Now when I add 17 to -12 minus 16, I just add the real parts. 17 and -12 becomes 5. I now get to do this multiplication again. 1 minus 2i times 5 minus 16i. So I get 5, negative 16i is outside, negative 10i is inside, 32i squared is outside. So that's negative 32 plus 5 is negative 27 minus 26i. Again, add the real parts. 14 and negative 27 is negative 13. I'll do my multiplication. Again, lots of space required because there's a lot of foiling on these. But I'm just multiplying complex numbers. It can be done. There's a lot of room for error, though. So you have to be careful when you FOIL. 1 minus 13. 1 times negative 26i is negative 26i. 2i times negative 13 is negative 26i plus 52i squared gives me negative 52 and negative 13 is negative 65 minus 52i. Wait a second. Oh, wait, no, this is a plus 26i. I messed up when I did negative 2i times negative 13, that's plus 26i. So that actually cancels out and I just get negative 65. Which gives me a remainder of 0, which is important. I should get a remainder of 0 because this is a root. Okay. And so when I didn't, I look back and go, I must have made a mistake. They told me this was a root. I better get a remainder of 0. So I got to check and figure out where I made a mistake. Hopefully it's in the last one. So now I can take my other root, 1 plus 2i, and I'm going to divide it by my answer. I don't need to check the first one again. It's almost for sure it doesn't work twice. And with a fourth, I know that this 1 plus 2i does work. So it will be a quadratic after I've pulled out 2 factors. So 4, bring it down. 1 plus 2i is 4 plus 8i. Now when I add these, 4 and 4 makes 8. Negative 8i and 8i is 0i. 1 plus 2i times 8 is again 8 plus 16i. 5 and 8 is 13. 13 times 1 plus 2i is 13 plus 26i. This one ends up being easier, and I end up with real coefficients for x squared plus 8x plus 13. Now I want to find those roots. So I'm going to use the quadratic formula. Need a new page. And I know I'm going to write my roots here, so I'll use them again. So x equals negative b, that's negative 8, plus or minus the square root of b squared. 8 squared is 64. Minus 4 times a is 4 times 13. All over 2 times 4. Okay, let me grab a calculator because I don't know 16 times 13. Yeah. So it's 64 minus 208, which is negative 144 in that square root over 8. Square root of 144 is 12. The negative is 12i. Oh, I forgot my plus or minus. Oops. I can reduce. Now, each one of these is a factor of 4. When I reduce, I must go from all 3 of these terms. Bring me -2. I'm dividing each one by 4. Over 2. Or I can split this up. And it's going to give me these results. Negative, which equals -1 for -2/2, plus 3/2i, and comma, -1 minus 3/2i. Again, these are conjugates. They're differentiated by the sign. My linear factors. X minus 1 minus 2i is actually x minus 1 minus 2i. So I'm using double parentheses here. That's actually x minus 1 plus 2i. But the next one is x minus 1 minus 2i. So I usually don't even bother to write them out. Since it's conjugates, I know I'm going to have both of these signs here. My other ones are going to use the ones below. X plus. You always have to switch the first sign. So because this was a -1, it's got to be x plus 1 plus 3/2i. X plus 1 minus 3/2i. Your conjugates must come between the complex numbers, not the sign in the middle. Okay. Factoring as a product of linear factors, example 6. Gives me this. Okay. Plus so this one, they suggest looking at the graph first. And using your graph to find some zeros. This one right here is 2/3. Okay. So I'm going to do 2/3. That would show up in my list as possibility of 16/3. Can you guys please be quiet? I'm recording. It's okay. 3 times 2/3 is 2. 2/3 times 0 is 0. 6 plus 0 is 6. 6 times 2/3 is 4. 0, 0, -24 times 2/3 is -16. And this works. So I know I've got a factor of x minus 2/3. Likely what I'd like to turn that into, since I've got a leading coefficient of 3, well, and I know I have 3x to the 4th plus 6x minus 24. I can factor a 3 out of the x to the 4th thing. Factoring out a 3 gives me 8. I'm going to distribute the 3 into the x minus 2/3, giving me 3x, and 3 times -2/3 is -2. I'm going to factor this. I missed a squared there. There is a squared on the 2x squared into x squared and x squared. Can you please be quiet? I'm recording. Okay, thank you. X squared and x squared is going to give me x to the fourth, and it will give me middle terms of x squared. Plus and minus adds to -8, or multiplies to -8 and adds to 2 is +4 and -2. Okay, can I factor this further? Sure, x squared plus 4 equals 0. When I solve, I get x squared equals -4. X squared equals plus or minus 2i when I square root both sides. This one, x squared minus 2 equals 0. X squared equals 2. X equals, when I square both sides, plus or minus square root of 2. Giving me a result of 3x minus 2, x plus 2i, x minus 2i, x plus square root of 2, x minus square root of 2. And that is my result. It was really crucial that this factored for me to be able to find that by hand. The calculator could help, but it wasn't going to give me this plus square root of 2 and minus square root of 2. It'll give you decimals. You might recognize what they are, but you cannot use synthetic division to find with square root of 2. Okay, that is the end of section 2.5.